Hello, this is Professor Kuehn. In my previous lecture, I reviewed Huygens' principle. In this lecture, what I want to do is talk about how Huygens uses this principle in order to understand the law of reflection. Remember the law of reflection. This is something that Huygens, of course, did not come up with. It's something that was well known at the time of Huygens. And the law of reflection is that when you have a ray of light that is incident upon a reflecting surface, such as a mirror, that the angle of incidence is equal to the angle of reflection. The question that Huygens is interested in now is, why is that the case? Not merely that it is the case, but why is it the case that the angle of incidence equals the angle of reflection? This is what he's talking about on page 182 in his Student's Guide to the Great Physics text, where he's presenting an explanation of a law of reflection in terms of his wave theory of light. So what I'd like to do is step you through this proof that is depicted in figure 15.1 on page 182. This is in his chapter 2 of his treatise on light, on reflection. I've blown up the diagram and it's shown here, and I'll read and explain as I go. What Huygens says is that, having explained the effects of waves of light which spread in a homogeneous matter, that means a matter that is the same throughout, we will examine next that which happens to them on encountering other bodies. We will first make evident how the reflection of light is explained by these same waves and why it preserves equality of angles. That is, once again, why the angle of incidence is equal to the angle of reflection. So he says, let there be a surface AB in figure 15.1, plain and polished, of some metal, glass, or other body, which at first I will consider as perfectly uniform, reserving to myself to deal at the end of this demonstration with the inequalities from which it cannot be exempt. So he's saying here that this line AB represents a mirror, let's say, and he's going to assume that this line AB, or the mirror, is perfectly smooth. Later on, he's going to allow that there are rugosities or bumps, imperfections in the mirror, and he's going to show that that doesn't really matter. Okay? And then he goes on to say that let a line AC, which is inclined to AB, represent a portion of a wave of light, the center of which is so distant that this portion AC may be considered as a straight line. So here, this line AC is an incoming wave front, and it's at a particular moment in time. It's at line AC. He says, for I consider all this as in one plane, imagining to myself that the plane in which this figure is cuts the sphere of the wave through its center and intersects the plane AB at right angles. This explanation will suffice once for all. So this is sort of he's imagining that the surface of your computer screen or your sheet of paper is kind of a cross-section to this spherical wave that's expanding, so that we can approximate the wavefront as this line of the intersection between the sphere and the plane of your paper or the plane of your computer screen. He said the piece C of the wave up here, piece C up here, will in a certain space of time advance as far as the plane AB. So this point right here will advance along the line with all these little L's over to point B, following the straight line CB, which may be supposed to come from the luminous center. That is the light source that is way off to the upper left. That portion that's at C will advance along CB and strike the mirror at point B. So which may be supposed to come from the luminous center, and which is in consequence is perpendicular to AC. Now, in this same space of time, the portion A of the same wave, which has been hindered from communicating its movement beyond the plane AB, or at least partly so, ought to have continued its movement in the manner which is above this plane along a distance equal to CB, making its own partial spherical wave according to what has been said above. So in other words, this point A, right here, during the same time that the wavefront C goes over to point B, it will have continued along a line from A over to G. So it would have ended up over here near point G, but because there's a mirror, it cannot continue there. So instead, there's going to be a spherical wave that's spreading from point A that spreads out. And he says, making its own partial spherical wave, I'm reading at the top of page 183, which wave is here represented by the circumference SNR. So this wave right here, SNR, will be that spherical wave that is emanating from point A, and it's going to have the same radius as the line segment CB, because during that time interval, when the wavefront at C gets to B, the spherical wave spreading from A will have propagated the exact same distance. So that will be the wavefront. He says, which wave is here represented by the circumference SNR, the center of which is at A, and its semi-diameter AN is equal to CB. So this line segment AN, the radius of that spherical wave, is going to have the same length as a line segment CB. Again, because it will have taken the same amount of time to propagate away from point A as the time it took the wavefront point C to travel on to B. He goes on to say, if one considers further the other pieces H of the wave AC, so each of these little points in between A and C, these points here and here and here, maybe I'll make these different colors. So let's make this one right here blue, and let's make this one right here kind of a peach colored, and we'll make this one right here maybe brown colored. Okay, so if one considers further the other pieces H of the wave at AC, it appears that they will not only have reached the surface AB by straight lines HK, so this blue point H will have gone on to point K, and this peach point H right here will have gone on to point K, and this brown point H right here will have gone on to this point K during that same time interval. So they will have not only reached the surface AB by straight lines HK parallel to CB, but that in addition they will have generated in the transparent air from the centers, blue K and peach K and brown K, particular spherical waves represented here by circumferences, the semi-diameters of which are equal to Km. All right, so in other words, the point which had been at blue H and went on to blue K, by the time that the orange wave will have spread from A out to S and R, that point K will have spread out with a radius equal to length Km. So I'm going to draw that spherical wave like this, the blue one. Like that, whoop, along here. And the peach one, right here, will have spread out around there, like this. And the brown one, he's going to say, will have spread out like this. So notice the brown circle is smallest because it will have spread for the smallest amount of time. The peach circle will be second largest because it will have spread for the second largest amount of time. The blue circle will have spread for the third largest amount of time, and the orange circle will have spread for the longest amount of time. So he says, these particular spherical waves represented here by circumferences, the semi-diameters of which are equal to Km, the radii of which are equal to Km. That is to say, to the continuation of HK as far as the line BG parallel to AC. But all these circumferences have as a common tangent the straight line BN. So now what I'm going to do is I'm going to draw in yellow this straight line, and I'm going to extend it. Whoops, I didn't want to make it that color. I wanted to make it yellow. This right here, this is a tangent. They have a common tangent BN right here. Okay. Namely the same which is drawn from B as a tangent to the first of the circles, of which A is a center, and AN the semi-diameter equal to BC, as is easy to see. So all these partial waves are going to have this common tangent line. It is then the line, he says, BN, this line right here, that yellow line BN, comprised between B and the point N, where the perpendicular from the point A falls, which is, as it were, formed by all these circumferences, and which terminates the movement which is made by the reflection of the wave AC. So in other words, if this had been the incoming wave right here, and as it propagates, and the parts of it are striking at points A, K, 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 and they're generating spherical waves, the outgoing wave will be NB. and is also the place where the movement occurs in much greater quantity than anywhere else. That is, these spherical waves constructively interfere. Wherefore, according to that which has been explained, Bn is the propagation of the wave AC at the moment when the piece C of it has arrived at B. So by the time the point C has arrived at B, then this straight line Bn will be the outgoing wave. The wave C at the moment when the piece C of it has arrived at B. For there is no other line which, like Bn, is a common tangent to all the aforesaid circles, except BG below the plane AB. So this right here, maybe I'll make this one in green, this would have been the common tangent of all those circles. If the mirror wasn't there, the wave simply would have propagated from AC over to BG. But because the mirror is there, it's reflected up to Bn. For there is no other line which, like Bn, is a common tangent to all the aforesaid circles, except BG below the plane AB, which line BG would be the propagation of the wave if the movement could have spread in a medium homogeneous with that which is above the plane. And he goes on to say, if one wishes to see how the wave AC has come successively to Bn, one has only to draw the same figure, the straight lines KO parallel to Bn, and the straight lines KL parallel to AC. Thus, one will see that the straight wave AC has become broken up into all the OKL parts successively, and that it has become straight again at NB. And he goes on to say, now it is apparent here that the angle of reflection is made equal to the angle of incidence. So this line right here, Bn, makes the same angle with respect to the surface as the line CA had made with the surface. For he says the triangle ACB, so this triangle, maybe I'll make this one in light blue, this triangle ACB, that triangle, ACB, says for the triangle ACB, BNA being rectangular and having the side AB common, so BNA, this triangle right here, this blue one, he said these ones, because they have a common hypotenuse, AB, and because they share common angles, they are similar, they are congruent triangles. He says ACB and BNA being rectangular and having the side AB common and the side CB equal to NA, it follows that the angles opposite to these sides will be equal. So these angles right here, if I were to draw in deep blue, this angle right here is going to be exactly the same as this angle right here. So these two angles are going to be equal to one another because they share the same hypotenuse and they share the same opposite side. And therefore also angles CBA and AB. But as CB perpendicular to CA marks a direction of the incident ray, so AN perpendicular to the wave BN marks the direction of the reflected ray. Hence these rays are equally inclined to the plane AB. So in other words, the angle of incidence equals the angle of reflection. So he has provided here a geometrical proof based only on Huygens' principle and the wave theory of light, that from which follows the law of reflection of light. Okay, now in the following page, on the following page, what Huygens is going to do is he's going to generalize this and say, although we've considered kind of a plane cutting through this incoming spherical wave so that we can use straight lines here, we could generalize this to a broader wave as shown in figure 15.2, and he says that will not affect the proof whatsoever. I'm not going to go through his explanation there, but finally at the bottom of page 184, he says the nice thing about this is that even if you were to allow tiny bumps or rugosities or imperfections in the surface AB, it would not significantly affect the proof, because all that this really requires is that the incoming wave excites the particles of the mirror so that they emit spherical waves or spherical wavelets. And it doesn't matter if one of the wavelets is slightly higher than the other one on the surface, these will all interfere in such a way to give the angle of incidence equal to the angle of reflection. And he says that this is not the case if you think of light as a particle. This is what he mentions at the top of page 185. He says, for the surface, consisting thus of particles put together, and the ethereal particles, the ether, above it and smaller, it is evident that one could not demonstrate the equality of the angles of incidence and reflection by similitude to that which happens to a ball thrown against a wall, of which writers have always made use. So if you consider a bumpy mirror and you think of little particles of light hitting it, they will bounce off in kind of funny directions, almost like if you were to throw a baseball at a metal corrugated wall. If it had bumps on it, the baseball would bounce off in kind of a funny direction, so the angle of incidence is not the angle of reflection. So the particle theory of light, he's here arguing, it suffers from problems in accounting for the law of reflection in the way that his wave theory of light does not. He says, in our way, on the other hand, the thing is explained without difficulty. For the smallness of the particles of quicksilver, mercury, for example, being such that one must conceive millions of them, and the smallest visible surface is proposed arranged like a heap of grains of sand, which has been flattened as much as is capable of being, this surface then becomes for our purposes as even as a polished glass is. And although it always remains rough with respect to the particles of the ether, it is evident that the centers of all the particular spheres of reflection of which we have spoken are almost in one uniform plane. And he says that this accounts for the law of reflection. Okay, I'm going to stop there. The next time, we're going to talk a bit more about chapter 16 and how Huygens' principle can account for the law of refraction.